Hi everyone, this is Debasattam and you're watching the second lecture of EE635 Applied Linear Algebra. As you might already be aware, we are conducting our course completely online this semester because of the pandemic situation. Uh, so our primary platform for communication and making announcements, assignments, all these things. So the primary platform is going to be Google Classroom. All of you have already hopefully joined the Google Classroom. If in case you have not, then please let me know. Send me an email or call me up personally. I will try and see what I can do. Our secondary platform for communication would be Moodle. Yeah, so same thing applies to Moodle also. If when you log into Moodle, if you don't see this course, although you have registered for this course, then please let me know. I will see what I can do. Yeah, I will certainly add you up. If your name does not appear, then we'll see what to do. Okay. Now, let us get on with the proceedings. But before that, I would like to remind you that in addition to these video lectures, we are also having live interactive sessions according to the stipulated hours given by the institute timetable, which happen to be Mondays and Thursdays from 5:30 p.m. to 6:55 p.m. every week, right? And the link for the Google Meet for these meetings would be the dedicated Google Meet link that we have for this course. That link also is something that you will be able to find out when you log into your Google Classroom via LDAP login. Yeah, on the cover of this course, this information for the Google Meet link, the dedicated link, would be mentioned. Okay, now this is what I can remember as of now. If something comes up, I will let you know in between. Okay, so now let us get on with the proceedings. So what we've been looking at is linear, okay, systems of linear equations, yeah, which are just simply called AX equal to B systems, right? Where A is a known matrix, B is a known vector, and X is an unknown vector to be found out, right? But the question is, how do we actually solve these equations? We have already seen three different cases, as different as they could be, where these equations appear, namely for electrical networks, yeah, then for once you discretize a partial differential equation by finite difference method, and discrete Fourier transform. In all cases, and of course there are so many others also, in many such cases, you get equations of the type AX equal to B. The question is, how do we solve them? That is what we will concern us in this lecture. Okay, so let me try and share my screen here so that we get the whiteboard, and then we can start. Okay, then we can start working out this one step at a time. Okay, so let me jolt your memory. We are looking at equations of the type AX equal to B. Right, so I have AX equal to B is what we would like to solve. As I've said, A is a real matrix of size M cross N. B is a vector of size M, so these are known. We have to find out this unknown vector X, which we want to be in Rn, but we don't know what X is. How do we do that? How do we solve this? Yeah, one crucial first step for this would be to expand out this equation. Yeah, so what is it? So the equation actually looks like A11X1. So this is something that will come up every now and then. So that is why I'm spending time in writing it out explicitly, because we'll be needing it again and again and again. 1nxn equals b1. This I can call equation number 1. And then I have a21 x1 plus a22 x2 plus dot 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 to plus a2n xn equals b2, which is equation number 2. This continues like this. I finally have a m1 x1 plus a m2 x2 plus dot 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 plus a mn xn equals bm. So this is my equation number m. Yeah, so I have this set of m equations. The matrix vector notation of this is a11, a12, dot 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 up to a1n, a21, a22 up to a2n, then am1, am2, amn. Then by the rule of matrix vector multiplication, you know that if I write my vector like this, then this is just another representation of the same system of equations. That's why we say that Ax equal to b is actually a system of linear equations. The question is, how do we solve it? I'm sure you have seen how to solve this before, namely for 2 by 2 systems, 3 by 3 systems, right? When A is a 2 by 2 matrix or a 3 by 3 matrix, or maybe 4 by 4. What was the technique? You have Ax equal to b. The crude way of solving this is, first step, find out determinant A. Check if determinant of A is not equal to 0. If yes, if determinant is indeed non-zero, then compute A inverse by defining it as adjugate of A divided by determinant of A. What is adjugate? As complicated formula. So adjugate of this entry would be the determinant of this one. Adjugate of this entry would be, you get rid of this this column, this row, this row, this column, whatever is left, find out the determinant of that, and then with a minus sign, that would be the adjugate. Okay, that would be adjugate of this entry. Yeah, complicated formula. I also don't remember what it is, but that is how you did. But think of doing this for, say, a 10 by 10 system. Even if you can do it, think about doing it for a system which is, say, 10,000 by 10,000 or a million by million. How will you do it? Even to write down a formula for that, even to write down a computer code for that is tedious. Even if you can do some sort of recursive algorithm for, for finding out this inverse using this formula, it's going to take immense amount of time. Yeah, because so many computations have to be done. Even to calculate the determinant, you have to do so many calculations, right? It's not worth it. Yeah, but it turns out that instead, something that you may have learned before may actually come useful. Yeah. Think about this other situation also, that if it is square, then you can find out the determinant. Okay, but what if the system is not square at all? Then what will you do? Yeah, in that case, the determinant is not going to work out. The determinant does not even exist. If it's let's say as we say, a fat system, less number of rows, more number of columns. But even then, in that case also, we'd like to solve these equations, right? What can we do in that scenario? Before we proceed, it would be important for us to define what we mean by solution of an equation, of a system of equations, because we are saying we have to solve it, no? So what do we mean by a solution? So suppose xi is a vector. Yeah, xi in Rn is a given vector. It's not a variable anymore. It's a vector. So xi in Rn is said to be a solution, said to be a solution to the system of equations Ax equal to b if xi satisfies xi equal to b. That means you replace x by xi, it satisfies the equation x equal to b, right? Understandable. Yeah. With that, one can also define the set of all solutions, which we call the solution set. What would be the solution set? Solution set S is defined as follows. It is the collection of all solutions in Rn. This is a typical description of a set. This is where you write down about the elements of the set. What are the elements? And this is where you describe the qualifying property. So this is the property which will determine whether an element qualifies to be within the set or not. Right? So this is the solution set. Now, so the question remains, given system of equations may not necessarily be a square system, how do we get all the solutions? Yeah, that is the question. Well, we have looked at one way for the square case, taking determinants. But when did we learn this determinant and taking inverse like this? Perhaps in our bachelor's, no? But trust me, we've been solving linear systems of equations even from before. Yeah. Namely, when we were perhaps in 9th standard or 10th standard, we were solving simultaneous equations, no? 2 equations at a time. They are also linear systems of equations. And it turns out that one of the methods that we used for solving those simultaneous equations is actually much more sophisticated than finding out determinants. Yeah, indeed. The elimination of variables is that method. And it turns out that that elimination of variables method is actually going to work out even here. Yeah. Now, what was that method? Elimination of variables. If you remember, so let me just jolt your memory a little and tell you what this method was. Yeah, let me remind you. It was in fact something like this. I have a11 x1, although we called it x and y then, but now we are a little more sophisticated, so I'm going to use x1 x2. a11 x1 a12 x2 equals b1. That is my equation number, what should I call it? Say 1 again. Don't get confused with this one and the earlier one. Will make sense from the context itself. Okay. And then suppose I have a21 x1 plus a22 x2 equals b2. What did we do in order to solve this? What we did was we said that, okay, multiply equation number 1 by a21 and subtract from it a11 multiplying equation number 2. What does that give us? It gives us actually a21 a11 x1 plus a21 a12 x2 equals a21 b1 minus a11 a21 x1 minus a11 a22 x2 equals minus a11 b2. Yeah, I think I have done it correct. Yeah. Now, lo and behold, these two are the same. That is how they have been designed. That is why I did this multiplication. And because they are the same, I can just cancel them out. What I'll be left with then in that case would be a21, a12 minus a11, a22 into x2 equals a21, b1 minus a11, b2. Yeah, which is an equation purely in terms of x2. Which means I can now solve for this x2, provided, of course, that this quantity out here is non-zero. If this quantity is non-zero, then I can just divide by this and get x2. And once I have x2, I can just do a substitution of this value either in equation 1 or in equation 2 and get a value for x1. That is how we solved. That is how we eliminated this x1 variable. But now, also, it's important to notice here is that this being non-zero actually means the determinant is non-zero, because this is nothing but the determinant. This quantity here is nothing but the determinant. This is in fact the negative of the determinant. But this is zero if and only the determinant is zero. So therefore, if the determinant is non-zero, then I can use this elimination and get a solution for x2, and then do a substitution and get a solution for x1. Yeah. How do I mimic this, or how do I do this for okay, how do I do this for the uh, for the general system of equations also? Okay, now here is the thing. Notice what I did here. This is going to be important. This is what we call a linear combination of the equations. It's a linear combination. This phrase, linear combination, is something that's going to show up multiple number of times throughout this course. Oops, I wrote two O's. I don't know why, but I did. Linear combination. So much so that it makes ample sense to actually go ahead and define, go ahead and define this as an abbreviation, LC. So this is what we have for, this is going to be important for us, linear combination. Now, what is a linear combination? A linear combination essentially means the following. Okay, say I have, so once again, go back and recall that we have equations given by a11x1, a12x2 plus dot 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 up to a1n xn equals b1. This is my first equation. A21 x1 plus a22 x2 plus dot 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 plus a2n xn equals b2, and continues like this. I have am1 x1 plus am2 x2 plus dot 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 up to amn xn equals bm. I have called this my equation number 1, this is equation number 2, and so on up to this as equation number m. When I have linear combination, it means the following. Linear combination of two equations is, say, alpha 1 times equation number 1 plus alpha 2 times equation number 2, where alpha 1 and alpha 2 are given real numbers. Okay. Now, what does this mean? Alpha 1 is a real number, alpha 2 is a real number. So this means this new equation, so this linear combination, so alpha 1 times 1 plus alpha 2 times 2, this happens to be what? This in this case will be alpha 1 into a11x1 plus a12x2 plus dot dot dot. Thank you, the dogs have stopped barking. They're making my life absolutely miserable. Oh, they have started again. There's no escaping, looks like. Let's see what we can do. This is, but now let's say I don't write this equal to alpha 1 b1 as yet. Instead, this is summed with alpha 2 a21 x1 plus a22 x2 plus dot 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 up to plus a2n xn. This now would be equal to alpha 1 b1 plus alpha 2 b2. So this is a new equation which I have obtained by taking the given linear combination, where alpha 1 and alpha 2 are some given real numbers. That's how I have taken a linear combination. Yeah, this is a linear combination. Now, of course, by a little flight of imagination, you can now consider linear combinations of n equations. There's no harm in it, right? So now I can look at linear combinations like linear combination of m equations. Yeah, alpha 1 into 1 plus alpha 2 into 2 plus dot 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 up to alpha m into m. Yeah, this is also fine. How is it going to look like? Well, alpha 1 into a11x1 plus dot 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 a1n into xn plus alpha 2 a21x1 plus dot 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 a2n xn plus dot 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 alpha m am1 x1 plus dot 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 plus amn xn must then be equal to okay, no bracket, alpha 1 b1 plus dot 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 alpha m bn. That's the linear combination. Yeah, now I do a little reshuffling, little juggling of these numbers. Yeah, and I can write something which looks really sophisticated. Yeah, this is equivalent to summation I going from 1 to m alpha I a I1, this summation now into x1 plus summation I going from 1 to m alpha I a I2 x2 plus dot 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 plus summation I equals 1 to m alpha I a I n xn equals summation I going from 1 to m alpha I bi. Yeah, that's it. Okay, this is my equation m plus 1. So I have formed a new equation m plus 1 by looking at this linear combination, right? Now I make a small observation. Yeah, I make a small observation. This is going to be crucial for us to proceed further. The observation is the following. Let xi be a solution of ax equal to b. That is, it's a solution to the common solution, a common solution to equations 1, 2, dot, 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 up to m. Mathematically, xi belongs to S, the solution set of the given equations. Then xi satisfies equation m plus 1. Very simple. Proof, in fact, the proof is kind of trivial. I'm sure you already see why this should be true, how to do this proof. Okay, so look at left hand side. Left hand side is in xi satisfies equation m plus 1, right? So I just have to plug in xi for x1 up to xn in equation m plus 1 and show that it satisfies. So the left hand side equals the right hand side. So first look at the left hand side. What is the left hand side? Left hand side is summation I going from 1 to m alpha I a I1 xi1 plus summation I going from 1 to m alpha I a I2 xi2 plus dot 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 plus summation I going from 1 to m alpha I a I n xi n, right? This is the right hand side. But then we have already seen that this is nothing but alpha 1 into a11 xi1 plus dot 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 a1n xi n plus alpha 2 a21 xi1 plus dot 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 a2n xi n plus dot 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 alpha m a m1 xi1 plus dot 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 plus a m n xi n. But xi is a solution, so this is nothing but alpha 1 into b1 plus alpha 2 into b2 plus dot 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 up to alpha m into bm. That is precisely equal to the right hand side, so proved. Which then also means that if we have a new equation, we have an equation that is c1 x1 plus c2 x2 plus dot 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 up to cn xn equals d, where this new equation, which is a linear combination of equations 1 up to m, then xi belongs to S implies xi satisfies C1 xi1 plus C2 xi2 plus dot 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 up to Cn xin equals D. So crux of the matter, if I have a system of equations and I know some solution, then that solution automatically will satisfy any linear combination of those equations. Right? So if I form new equations by taking linear combinations of the old equations, they will certainly satisfy. So any solution of the old system will certainly be a solution of the new system also. Okay, how does this help us really? Once again, little flight of imagination. Yeah. So think of the situation we had. What did we do? Somebody gave us equations. I formed a new equation by taking linear combination. But no one should stop me. No one can stop me from taking more equations, right? So I have m equations. From there, taking linear combination, I form one more equation. I can form another new equation by taking linear combinations. I can take another equation by taking linear combinations. So I can form as many number of new linear equations as I feel like. Yeah, no one can stop me from doing that, which means I can form a new system of equations, which means I can now have different systems of equations. And that is where this thing comes in, namely equivalent systems. So equivalent systems. Because we're talking about equivalent system, that means obviously there will be multiple systems. So say I have system 1, which is given by ax equal to b, and I have system number 2, which is a hat x equals b hat. Right? Now, if I have these two systems, I say that once again the dogs are at it. So, okay. System 1 and system 2 are said to be equivalent if every equation, so notice carefully, every equation in system 2 is a linear combination of equations in system 1, and importantly vice versa. That means every equation in system 1 also in turn is a linear combination of equations in system 2. Remember, when we are looking at this equivalent systems, system 1, system 2, their sizes need not match. The number of variables in X should certainly be the same, of course. So that number is n. So matrix A and A hat both will have n number of columns, but the number of rows may be different. No one imposes that the numbers are same, right? But even then, what it is saying is the following, that if every equation in system 2 is a linear combination of equations in system 1, and every equation in system 1 in turn is a linear combination of equations in system 2, then the two systems are equivalent. Yeah, this then brings us to the first theorem of this course. Wow, the dogs are at it again. I don't know what I can do. Who knows, maybe a leopard has shown up. That's why they are barking so much. Okay, theorem. Very intuitive, very interesting statement. Theorem. AX, okay, let me write it down properly. System 1, AX equal to B with solution set S1, and system 2, A hat X equals B hat with solution set S2 have exactly same set of solutions, that is S1 is equal to S2 if sys1 and sys2 are equivalent. That means in one sentence, equivalent systems have exactly same set of solutions, exactly same solution set. Yeah, how do we prove this? Proof is in fact very simple. This is instructive. Whenever we have to show proof of two sets, prove that two sets are equal, the trick is to show that one set is containing the other. So that means we have to first show that S1 is contained in S2. How do I do this? Well, let Xi be an arbitrary element in this set. Yeah. Now then, okay. By observation, this observation. Oh, by the way, this is an observation and this one is theorem. So this course, caveat, huh? This course is going to be a mathematical course. So we are going to have these, we're going to see these theorems left, right, and center everywhere. Again and again, we are going to see these theorems. Yeah. We are also going to see something called lemma. Yeah. What is a lemma? Lemma is also like a theorem, but not quite. In what sense? Well, a lemma may be a short result, may not be that profound, but important. Technical, too much computations is required, but it's not profound. It does not say something really, earth-shattering. Unlike, like for example, this theorem, it says so interesting and profound statement: equivalent systems have same solution set. Yeah, but this observation is like only for a particular, look at equation and then take one linear combination. Then if one, if Xi is a solution of the original equations, then it is also it also satisfies the linear combination. So not so profound. Such a thing is called a lemma. Yeah. So in this case, it's we are completely justified in calling this guy as a lemma. Okay? A lemma. Mathematicians can be very, what should I say? There's a word called pedantic. People who worry too much about small, small things. Pedantic. Mathematicians can be pedantic at times. And this is one example that we don't call every result a theorem. Some results is also a lemma. Or some result is also a lemma. Okay. Right. So now, why did I broach this subject? Because I'm going to write something like this now, that let Xi be in S1, be arbitrary. Then by our lemma, Xi must satisfy every equation in system 2 because these equations are linear combinations of equations in system 1, right? So therefore it will satisfy every equation in system 2 because they are linear combinations, but then this implies psi is an element of S2. That's it. Now we have to show S2 is contained in S1. The proof is going to be exactly the same by the same logic, by lemma, same logic applies. Complete this as a homework, right? Okay. Let us put an end to this discussion now. So this is going to be your module 1. Before we proceed to module 2, before you watch module 2 video, I would like you to try out this problem. Okay, so nomenclature. IA1 means immediate attention. So that means at the end of every module, I'll give problems which are such that you have to solve those problems in order to proceed to the next module. Yeah, so therefore these are of immediate attention. So here I'm giving one problem for immediate attention, which means you have to solve this before you go to module 2. What is that? Suppose I have this one system of equation and this another system of equations. Yeah, show that. Okay, question: are these two systems equivalent from the definition that we have seen about equivalence? If yes, then why? If no, then why? Together with these immediate attentions, I'm also giving homework problems, which are not something for you to immediately prove and then you can proceed to the next lecture. But instead, there's something that you need to ponder over before you come to the live interactive session, because there will be questions from this homework problems for the live interaction session. Here I'm saying that consider system 1 like before, find another system which is not equivalent to this one, right? So this is your homework problem. So do this. I'm going to show this again so that you can pause and solve this problem. Yeah, this is one. Pause it, look at it, and this is the other. Is it possible to show them all together? Let me try. No, not much, not as such. Yeah, but I think that you'll pause and get this. Okay. So all right. So that's a little pause for now. Let's meet for module number 2 in a short while. Okay. Till then, take care.